Okay, today's UML diagram is one of the simplest of UML diagrams, which is called state diagram. So let's discuss this. So I'm going to open up your reference book, Teach Yourself UML in 24 hours, because the slides they have provided by Colombo University is also based on this chapter. I mean, the contents are based on this. So what I'll do is I'll walk you through the important concepts that is needed for your syllabus in this chapter from this book, and then there are some minor examples, minor points highlighted in the slide as well, which I'll go through. Okay, so state chart diagram. Okay, let's begin by reading some of the stuff here. Second paragraph onwards. Each year brings new styles in clothes and cars. Seasons change the color of leaves on trees. Second example. Third, and passing years see children grow and mature. So these are some daily, not daily, I mean the natural things we observe in things that happen. What they're telling is certain objects in the real world, they don't stay in one state alone. They keep on changing, right? So when you take a cloth, maybe the cloth will change. Maybe the car, its conditions will change. If you take at natural trees and plants, the color of the leaves is not going to be green forever, right? They change state. Similarly, children, if you look at children like from baby, child, maybe a teenager, like that, you can see as a human being, they also change states. So without becoming any more like a greeting card. The point is that as time passes and events occur, changes take place in the objects around us. This also holds true in any system. As the system interacts with users and possibly with other systems, the objects that make up the system go through necessary changes to accommodate the interactions. If you are going to model systems, you must have a mechanism to model change. In your system, you will have some objects which will not be in one condition, right? It will keep on changing. We'll discuss that further with some more examples. So before that, we'll try to understand how state diagram is coming and what it is. One way to characterize change in a system is to say that its objects change their state in response to events and to time. Here are some examples. One thing, when you throw a switch, so throw a switch means they are saying you go and use your finger, a light changes its state from off to on. So the object is switch. So the switch can be in two states, either on or off. Similarly, if you take a remote control, a television changes its state from showing you one channel to showing you another. So if you take television as an object, one time it's showing one channel, then it goes to changes its state to another channel. Maybe it changes to off mode. Right? I mean, when you press the off button, it goes to off. So that is one example to understand. In washing machine or in this electronic ovens, you can see you have different states. Now, for example, washing machine, after an appropriate amount of time, washing machine changes its state from washing to rinsing, right? Then rinsing to maybe like spinning, then from spinning to stopping, and maybe then leaving out the water, right? Like that, you can see the washing machine is going through many states. So you can see that state. So to show these different states, we need a UML diagram. So for that, we use state diagram. So UML state diagram captures these kind of changes that happen in a single object. Keep in mind, state diagram captures the changes that happen on a single object, right? So it presents the states an object can be in along with the transitions between the states, and shows the starting point and end point of a sequence of state changes. That means looking at a state diagram, you have some other things that come around, just not the states. From one state to another state, when you're changing, you have to have a transition line. That means it will indicate what is happening, or what was the thing that is causing this to change from one state to another. And also maybe overall in that object, in terms of the states, what is the starting point, what is the ending point, right? So all these are indicated in a state diagram. Let me go here. Okay. So bear in mind that a state diagram is intrinsically different from a class diagram, an object diagram, or a use case diagram in a very important way. The diagrams that we have already studied, for example, class diagram, object diagram, or use cases, what are they doing? They model a group of class, group of objects. That means when you say persons, representing person, it's a group of things that represent many people, then you have a class called person. Then a state diagram. So then again, if you take object, it is similar. Then if you look at a use case also, you have in the use case diagram many use cases. It's not just a single use case in the use case diagram. So state diagram is a different thing. State diagram, as I told, a state diagram shows the states of a single object. So I would like you to kind of take a note of this statement, which can be easy for you to distinguish. A state diagram shows the states of a single object. Now I'm going to ask you a simple example, very simple example. Now imagine you have an object called, you're designing a system, let's say hotel reservation system. So in that you have a object called hotel room. Can anyone say what could be the states of a hotel room when you are designing a hotel reservation system? States of a hotel reservation system. I mean, states of a hotel room in a hotel reservation system. Okay, others, meanwhile, can you answer the question? Now you have a hotel. In the hotels you have rooms. So hotel room is going to be an object in that system, overall system. What are the states it can be in? Simple, few states. No idea? Now just think about the example I mentioned about switch you see in the wall. So in the switch switch I explained, switch can be in two states, on, off. Television we saw, it could be in on, it could be in one channel, then another channel. Right, washing machine we saw, when you start the washing machine, it can be in washing mode, it can be in rinsing mode, anything. If you take an example of a mobile phone, maybe mobile phone will be in standby mode, or it might be it might be idle, or it might be active, right? So in hotel room scenario, very simple. So either the hotel could be, hotel room could be, I mean, I'm not talking about a hotel room. If you take a single object, a hotel room could be either reserved, or it can be cancelled, or it can be occupied, right? So all are different states. When you say reserved, that means nobody else can come and book it. Another one would be cancelled. So maybe the room is free. It is, I mean, it was already booked, but now it is cancelled, right? Or it can also be in available state. That means now nobody has used the room, so it might be currently available, right? So this is how you see. You will take a single object in that domain and see what kind of different states it can be in, right? So we'll look at some examples as we go. Let me see if I can show you. Let's see, here is they are given the same example in your slide as well, right? So maybe at the beginning you have a starting point. I will explain these notations. So it is in available mode, available status. It can go to occupied status. It can go to reserved status. And again, maybe back to available status. A different variation of the hotel room in a different scenario. Maybe requested is one state, confirmed, used, archived. So single object that can go into different status. Here is a state diagram for course class related to courses. So course can be initialized, it can be closed, it can be opened, it can be cancelled, right? So you look at a single object in your overall problem domain and you identify the states. Okay, so how do you draw a state diagram? How do you draw a state diagram? Is what we're going to discuss now. We have mentioned, let me go to, okay, so this is the very basic notation of a state diagram. So what it will have is, in overall, you will have a dark circle like this, which indicates the starting point. And you have, after all the states are there, at the end, you will have a bullet point like this, which indicates the end point. And this kind of a box, you represent the state, whatever the state for that object. And these arrows indicate the state transition. Like for example, in this very simple one, your starting point is this, and it's going through a transition into some state. Then maybe if this is the last state of that scenario of that object, it transitions to the endpoint. Right? Additionally, you can, when you are writing something on this, so if you just have the name of the state, you just put it in the middle. Within a state, if you take a particular state, within that there could be more than one activity happening. When an object is in a single state, there could be many things happening within that state. So for that, we divide it like this and show it like this. We put the name at the top and then the set of activities at the bottom, right? So activities also vary, which we'll be discussing in a few moments. So let me go back to the note. So again, I'm reminding, we draw state diagrams not for all the objects in one diagram. We draw state diagram for a single object that could have multiple states. Right. So that figure which we discussed shows the rounded rectangle that represents a state, along with the solid line and arrowhead that represent a transition. The arrowhead points to the state being transitioned into. Okay. The figure also shows the solid circle, that means the dark one, that symbolizes the starting point, and the bullseye that symbolizes an end point. Right. Now we are going to add some details to these symbols. That means when we say details, like the text information, right? So the UML gives you the option of adding detail to these symbols. You can divide the state icon into two areas, as I mentioned. When you're going to add name and activities, you can divide it into two. The top area holds the name, which you have to supply whether you are subdividing the icon or not, and the bottom area holds activities that take place in that state. Okay, so something like this. Now we are going to discuss about activities when you are drawing the state diagram. Three frequently used categories of activities are entry, exit, and do. So maybe you can take another short note of it if you have a notebook with you. Three type of activities: entry, exit, and do. So what is entry? Entry means what happens when the system enters the state. Right? So for example, in the hotel room scenario, so initially you are starting. Now first state of that room would be available. Now from when somebody is coming and trying to reserve, when you're changing the state from available to reserve, so let's say this is reserve. What is the entry activity? What happens when the system enters the state? Exit means now when this one is going to move to another one, what is the thing happening? What happens when the system leaves the state? So that is called exit activity. And do means what happens while the system is in the state. So when you are active in that state, what happens? So for that we indicate it with a do. Right? And maybe there could be any other things necessary, but fundamentally these are the three activities that we indicate in a state diagram. Now to understand that, to understand how do we make use of these entry exit things, because generally people just focus only on the name part. Maybe even in your your second part 2 paper also, very rarely you have a question that asks about activities. But still, if it is provided in the requirements document or the case study, like mentioning what states go, and then maybe they will say when it is in this state, these are the things that need to happen before entering. Maybe after exiting, this should be the condition, or maybe what should happen when it's in a state. If you get something like that, it's good to have a knowledge about this concept. Very simple, I mean, not very complicated. So to understand how do you show these activities, a simple example. A fax machine is an object whose states have activities, right? Fax machine is taken as an object here. So it will have multiple states. So each state is going to have some activities. When it is sending a fax, that is, it is in the faxing state. In this state, when it is in the faxing state, the fax machine engages in the activities of adding a date stamp and time stamp to the fax, and adding its phone number and the name of its owner, right? So when it is in the faxing state, all these things happen. In other activities in the state, the machine pulls the pages through, paginates the fax, and completes the transmission. So again, in the single faxing state, these are the other things also happen, right? Then when it is moving to the idle state, after doing the faxing, now it is moving to idle state. The fax machine presents the date and time on a display. So simply it is only involving in these two activities. So to see this one here, they have put this in that name activity format. So faxing is, so the object is a fax machine. It has two states. One is faxing, one is idle. So between the two states, it is going to change. The one thing they haven't shown is the starting point and the ending point, right? Maybe in this case they have assumed that this is always going to keep on working, so directly they start with the first state and the next state intermediate. You can see they have shown the arrows. It can only move from between these two states. So here you can see for the faxing state, entry activities, key in remote fax number. That means you have to type the number, and when you're exiting, when you're moving from faxing to idle state, this is what needs to happen: complete the transmission. When it is doing the faxing activities, these are the activities that need to happen. Right? Adding date stamp, timestamp, adding phone number, donor, all these things will happen when this faxing is working. When it is in idle, the entry condition, entry activities, okay, this part is complete. Exit means when you are moving back to faxing, you have to start the fax, begin the fax. Apart from that, when it is in idle state, idle we simply can understand idle means standby, right? Just like switching off your TV from your remote control. So you will see that small standby button just lighting up. So when it is in idle state, these two activities happen. Is this clear up to this point? Okay, let me switch. Is this clear up to this point? Okay, cool. I hope others also understood. Okay. Now in these transitions, so transition means now we discussed about adding details to the state, so that's all with that. Now we are going to talk about how do you add details to these transitions, right? So how these transitions happen, and how do you add details to that? You can also add some details in the transition lines. You can indicate an event that causes a transition to occur. That means there should be a reason when the transition occurs. So we can indicate that, which is called a trigger event. And the computation. We could also indicate an action that is happening, right? That executes and makes the state change happen. To add events and actions, you write them near the transition line using a slash to separate a trigger event from an action. Sometimes an event causes a transition without an associated action. Sometimes an event causes a transition without an associated action. That means normally events happen through actions. When you do action, only an event triggers the object. But sometimes without an action also an event can happen. A transition can happen basically. Right? So that is what they're saying in the first point. Sometimes an event causes a transition without an associated action. And sometimes a transition occurs because a state completes an activity rather than because of an event. That means to move from one thing to another thing, not necessarily there should be a state, maybe after completion. For example, in this fax machine scenario, when the faxing activity is completing, it will automatically go to the idle. So you don't have to do a action like this. Now for starting the action, you have to dial the fax number now. So that is the action you are doing for making this state happen. But when it is finishing, you don't have to do anything. Automatically it might go to the other state. So that kind of transition is known as triggerless transition. So take a note of these keywords here. So under this one, what we were discussing was how do you add details to those arrow marks, right, in the state diagram. So one thing is you can indicate an event, or you can indicate the action, or sometimes you can even show a triggerless transition. Okay. Let's see how they show it in a real thing. Okay, so they explain it through an example. Another example. Let's take the GUI. GUI means this kind of interface you see in a normal diagram, right? Where you can use your mouse and buttons and all, right? So the graphical user interface you interact with gives examples of transition details. For the moment, assume the GUI can be in one of the three states, right? Your graphical user interface can be initially in the initializing state, working state, or shutting down state, right? So when you turn your PC on, boot up takes place. Turning the PC on then is a triggering event that causes the GUI to transition to the initializing state, because that is the turning the PC on is something that you do as an action, and that triggers some event that causes the GUI to transition to the initializing state. And booting up is an activity that takes place during the transition. As you know, when you are switching on the machine, so switching on is the action you're taking for changing the state of the laptop from off mode to the next one, initializing mode, right? Initializing state. So during that initializing state, what happens is a lot of things happen. So main activity is the boot up. As a result of activities in the initializing state, the GUI transitions into the working state. When you choose to shut down the PC, you generate a trigger event that causes the transition to shutting down state, and the PC turns off. So to understand this, you can see here for that simple scenario how they have drawn a state diagram. So this state diagram, who is the object? Anybody? Who is the object? For which object we have drawn this? For which object we have drawn this diagram? Yes, PC, maybe more specifically the GUI. So within the PC, GUI is an object. So the different states the GUI can be, yes, or maybe in this case we'll take it PC. Right. Now you can see we start with the dark circle, we turn the PC on, it has moved into initializing. During initializing, you can see we have used that same notation. The name is here, the activity that is taking place. So we show it with a do / this one. Then it goes to working state. Once in the working state, maybe the next state will be shutting down. So this is the action you are taking. So we showed the action here. So here also you can see we have written the action here. And finally it goes to the endpoint. Right. Right. There are some other things we can add, other details we can add to the transitions. Like now here, this is simply the name we discussed, or the action or event or the triggerless event. Apart from that, we can add guard conditions. Right. The preceding account of GUIs leaves a lot to be decided. That means it is leaving a lot of doubts, or how these things happen, kind of questions are there. So first of all, if you leave your computer unattended, or if you just sit idly by and don't type or use the mouse, a screensaver appears. So this is a general scenario now. If you don't use the machine, you will see after a couple of times, if you have enabled screensaver will appear. and rescues your pixels from potential burnout. To say this in a state change terms, if enough time passes without any user input, the GUI transitions from the working state into a state I didn't show. I mean, what the author is saying, I didn't show in the earlier figure, which is called the screen saving state. Now, if you take this example here, this is a very basic state diagram. But now, when you dig further, you will realize in a real scenario, if somebody is not working for a long time. So this is an overall thing of initializing, working, shutting down. Now, let's say during working and now person leaves the computer. Now that is not shutting down. When the person is leaving the computer, he is not working. And also computer will not be always working. So after some amount of time, it will go to the screensaver mode. So that is a new state. That's a different state. But again, how does that state transition happen? It happens based on a condition, no? So the condition is some time limit. So that kind of thing is called a guard condition. So very simple example. So the time interval is specified in your Windows control panel. It usually is 15 minutes. Any keystroke or mouse movement transition, any keystroke or mouse movement transitions the monitor from the screen saving state back to the working state. So here, this is the little extended diagram. You can see they have introduced a new state called screen saving. So when you are from working to screen saving, how do you show the transition? Is you show a guard condition like this with the, just like I think in some of the earlier diagram, in class diagrams also we have seen this kind of square bracketed information. Mostly we indicate the conditions here. So here maybe we will specify the actual amount of time in this particular example. So that is shown in the transition. And if you look at this one, going back to the working mode, maybe just like how we showed an action here also we have shown an action, right? So from screen saving to working mode, if you want to transition, what needs to happen is some kind of mouse movement or maybe typing something on the keyboard, keystroke. Okay. So in this example, from working to screen saving, that 15-minute interval which we discussed is the guard condition. When this condition is met, the transition takes place, right? So that's what we understood. I mean, we understand as guard condition. Let's see if you have an example here in your okay, here you can see, I don't know whether you can zoom this a little bit. Okay. Now this is for course, right? State diagram drawn for a course. So the course has a starting point, it has an ending point, and maybe multiple ending points. Because through different states, it can reach the end point. So from initialization, starting with initializing state. So when initialization, when it is transitioning from starting point to the initialization state, this is the activity that happens. Do. Right now you saw in the book they have used a slash instead of colon. They use a slash. This is also okay. Now, if this initialization to needs to transition to the open state, this is the action you're taking, adding student, but also you have kind of a condition happening. If there is a variable called count, you need to set that to 0. So you show the guard condition here, right? Or maybe the initial, no, this is not the guard condition. This is actually the action. Another set of things, just add student, and also this needs to happen. Okay. Now if you look at, once it has come to the open state, you can perform this action called add student with a condition. How many times you can see this arrow mark, you are already familiar. This indicates a what? What is this indicating? It indicates a loop, repetition, something that you can repeat. So until you have less than 10 amount, you can keep adding this, you can keep using this open state. So internally you can see the entry activities register student. The exit activity will be the increment count. That means if it has reached the limit, that is the exit activity. Then if you look at from moving from open to closed, moving from open state to the closed state, this is the condition that need to happen. If this condition is not met, it will not move to the closed state. So that is another way of understanding. Clear? Clear how to use guard condition? So this is another example. This was a very basic example we saw here. This is another good example we discussed here. Any doubts on this? How to use guard condition? So the key thing when you are using a guard condition is showing it in a square bracket, within a square bracket. Okay. Any questions on that? Is it a must to indicate the condition? If you have the condition, I mean, for example, very simple state diagrams maybe don't have, now it depends on the business scenario, no? If you have an object, now if that object wants to move from one state to another state, simple scenario would be you don't have any conditions. So maybe after it completes its activity in one thing, it will move to the next immediate state. But if you look at this example here, now if you want to move to initialization to open state, you have to perform some action here. That you will show it in this. So again, from initialization, you can even go to the cancel state. So for that, you can't use the same action. Maybe you have to go through a different action. Right? So this is triggered by actions. But if you look at this open state to closed state, okay, before that, if you look at open to cancel state also, you have to trigger the action called cancel. Then only it will go from open to cancel. But if you want to move from open to closed, that cannot be happening automatically. No, you can't make that happen through a use action. That has to happen through a internal automated process. So to make that happen, yes, the internal system oriented changes, you can see we indicate the guard condition. So guard condition, to understand in different way, mostly happens without user interaction, right? So you use guard conditions to change an object from one state to another state whenever the user action is not possible. I hope that will give you a clear idea. So we don't use guard conditions always. So in cases where the user cannot change the state from one thing to another, in those cases you can show the guard condition. Is that clear? Okay. Right. Let me switch back to the book. Okay, so that was about guard condition. So keep a note of that also, that basic idea. Substates. Okay. Simply as the name mentions, substates are states that are within another state. That means if you take a single state, let's say this working state, now you already learned activities. So activities is not substate. Activities are what are the actions that happen, the internal tasks that happen within a state. Substate means if you take a single state like this, like the working state, for example, within the working state, there could be internally many states inside, which have their own activities. So that is called substates. So simply, maybe in our other kind of diagram we discussed, like you have process, in designing we learned system design. You have process, sub-process kind of thing. So some kind of similar idea here. Within a state, if you have substates. So this model of the GUIs is still somewhat empty. The working state in particular is a lot richer than what we showed earlier. So they are going to discuss about this one. So high level, this is okay. But if you take now working state, it can have many substates. So that is what they're explaining here. When the GUI is in the working state, a lot is happening behind the scenes. Although it might not be particularly evident on screen, the GUI is constantly waiting for you to do something. That is typing a keystroke, moving the mouse, or press a mouse button, right? For example, these are the kind of things you are doing when you are in the working state. No? When the GUI is in working state, for example, now even in this scenario, I'm using my mouse, sometimes I'm using my keyboard. So all these activities I'm doing, all these actions I'm doing when it is in the working state. So for that, the system needs to register those inputs and change the display to visualize those actions for you on screen. For example, by moving the cursor when you move the mouse, or by displaying an A when you press the A key, right, in the keyboard. So any action you are doing has to go through different states while it is in the working state. Let's see how they show it. So before that, these substates can come in two varieties. One is sequential, the other one is concurrent. These terms also, I believe you are already familiar. So sequential means the order, some state transitions that happen in an order. So state A to state B to state C, there will be an order. So you can show the substates in, there could be substates working in an order, which is sequential. Concurrent means there could be a set of substates working in parallel. For example, let's say A, B, and C are states that work in sequentially. Then maybe E and F, state E and state F work together in a sequential manner. But maybe the first group, A, B, C, and the E and F can work concurrently together. Concurrent means at the same time, right? First of all, we'll try to understand sequential substates. So as the name implies, sequential substates occur one after the other. Recapping the aforementioned substates within the GUI's working state. So let's take that single state called working. You have internally these substates: awaiting user input, registering user input, visualizing user input, right? So these user inputs could be either mouse events, or it could be keyboard, whatever we are typing in the keyboard, right? So when the GUI is in the working state, internally these three states could happen. So it will happen in this order: awaiting, registering, visualizing, then again awaiting, registering. So it will keep going in a kind of a cycle. So user input triggers the transition from awaiting to registering. Activities within registering transition, the GUI, right. Activities within the registering transition the GUI into visualizing. After the third step, the GUI goes back to the awaiting. As I told, goes first, second, third, then back to the first. So to show that, if you look at this diagram here, so this is the overall working saw earlier in the GUI state transition, the overall working state, the bigger one. So internally, you can see these three states mentioned here: awaiting user input, registering user input. Second one, after this, visualizing input. Then you can see this arrow mark or the transition coming back to where? The first substate again, right? So in between, so if you have active, so within this maybe the detailed activities under input, you can show it with the, just like how you showed for the common state diagram. So the substate also you can show that. Otherwise, you can simply show the actions that are triggering this. So to move from awaiting to registering, some kind of input needs to happen. This input could be, as I mentioned, keyboard change, or it may be a mouse change or something. And visualize, right? So that is one thing about it. Similarly, if you look at this one, there is another set of states here at the same working state. This is another group watching the system clock, and if there could be an interval, based on the interval, it could update the display, then it goes back to watching system clock again. Now I should take these two groups. As you can see, during this working state, these first three also happen, also these two happen. So in this case, we call these concurrent states. This is what is called concurrent states. So shown in one picture. So when you say one thing goes in an order, after first, then this and this, we call that sequential substates. When you have parallelly two sequential substates happening, that is called concurrent states. So let's see. So that explanation is within the working state. The GUI isn't just waiting for you; it's also watching the system clock and possibly updating an application's display. That means more than one thing is happening in time. For example, an application might include an on-screen clock that the GUI has to update. For example, what they're saying is there could be a whatever you're now to understand this simply. Take this example here. This is what they're talking about. This second set is watching system clock is basically our timer here. Now, when I'm using the GUI, one thing is I'm moving my mouse, so that is indicated through these three states. But at the same time, time is also changing. Time is changing automatically internally. So that is another set of sequential activity, sequential state transition that is happening within the GUI. So that is indicated through the second state here. So it will keep on watching, and maybe now in this case after 60 seconds, so the interval would be 60 seconds, for example. After 60 seconds, this display is changing, going to change. So from 6.8, it's going to change to 6.9, right? So every 60. So that kind of conditions. So you can see how you introduce the guard condition. So somebody asked about guard condition. So this is another example. See, you show the condition here. Based on that condition, you're moving from this state to this state. Once it has updated, it is going to keep on watching the system clock again, right? And keeps on changing. Right? So that is concurrent. So that was sequential and then concurrent subsequent. Okay, so to finish up that discussion, all this is going on at the same time as the sequence I just discussed, although each sequence is of course a set of sequential substates. So if you take this first group, that is sequence, if you take this second group, that is also sequence, but both are happening together. To differentiate that in your state diagram, you split it with a dashed line or dotted line. That is how you show the concurrent states in a state diagram. Very simple. So the recalling something like this. Separating the working state into two components like this one and this one might remind you of something. That is, remember when I discussed aggregations and composites, if you recall those diagrams. When each component is part of just one whole, you are dealing with a composite. The concurrent parts of the working state have that same kind of relationship to the working state. For this reason, in this GUI example, the working state is a composite state. So a state that consists of nothing but sequential substates is also a composite state. Okay, so that is just additional information. You don't have to worry about the terminology. What they're saying is, now this working state is not a single state, but it is a set composition of many states that are inside, and then you have a grouping of those states. So these are a set of sequential states. This is another set of sequential states. Okay, this is not needed. The additional one. Right. UML 2.0, the new one, has added some new state relevant symbols called connection points. They represent points of entry into a state or exits out of a state. Here is an example. Right. Now, this is a little kind of varied scenario you will face when you are designing state diagram for an object, single object, right? Where you have to have this concept of connection points. So first of all, understand connection points. They represent something that entry into a state. That means when you are going to enter a state, you show a connection point in your UML diagram. And also when you're trying to exit out of a state, you will have another connection point. So examples, imagine a couple of the states of a book in a library. You take a book object, and the book object can be in multiple states. At first, it's residing on a shelf. That is one state. If a borrower has called in to reserve the book, a librarian retrieves the book and brings it into the state of being checked out, because now somebody is asking the librarian to reserve the book. Now he hasn't just physically come and taken the book, maybe over a call or maybe through the library system. The user is asking the librarian to reserve the book. So in that case, you have a state called being checked out. That means nobody else can come and now get that book. So that is one scenario, right? Now, if the borrower comes physically to the library, browses through the shelves, selects the book, and then decides to borrow it. Now, this is another scenario, right? Another scenario means now this is like directly is coming to the library. It enters the being checked out state. So it is in the same state. It is going to go to the same state, but this is in a different way. So either case, it is being checked out, but you can see it is entering that state through a different way, different entry point. So you can think of each way of getting to the being checked out state as going through a separate entry point. One more thing to be aware of, suppose the borrower has borrowed more than some allocated limit or allotted limit, or has a number of unpaid fines. Maybe he has to pay a lot of money out, the fines because of delays of previous books. If that is the case, the book abruptly exits via an exit point from being checked out state. That means it has to come out of this particular checked out state based on this condition, right? So to show that each entry point is modeled as an empty circle, exit point is encircled in X. The circles are on the board of the state diagram. So how do you show for this previous example? This is how you show for that book. So first state is residing on shelf. It is going to be into being checked out. So one entry point is indicated through the reservation action or like reservation condition, checked out. The other one might be the physical kind of way of being checked out. But again, now if there is a problem in being checking out because he's doing and now he has this other matters or other conditions are there, he has not paid money or some issue is there, we show that with the exit point called ended with this cross, right? So that's a new way of kind of showing the information, like a way of indicating multiple entry points or maybe multiple exit points as well. In this example, they have shown only one exit point. How a state can go out of it is how you show it with these connection points. Okay. So why are state diagrams important? The UML state diagram provides a variety of symbols and encompasses a number of ideas, all to model the changes that just one object goes through. This type of diagram has the potential to get very complex very quickly. Is it really necessary? In fact, it is. It's important to have state diagrams because they help analysts, designers, and developers understand the behavior of the objects in a system. A class diagram and the corresponding object diagram show only the static aspects of the system. They show hierarchies and associations and they tell you what the behaviors are, but they don't show you the dynamic details of the behaviors. So if you take class diagram and object diagram, it's a static, fixed kind of representation. They don't show you dynamic details, like the sequence kind of thing. They don't show that. That is why class diagram, object diagram, use case diagram are known as static diagrams. State diagrams come under the behavior or the dynamic diagrams. Can a state diagram can have more than one entry? Yes, of course. In this example, I explained, right? So you can see this state called being checked out can come through multiple entry points, either through reservation or through a physical activity of reserving the book. Right? So, for example, reservation means, as I told, maybe this can also have multiple reservation. Maybe let's say you can say reserve through phone, maybe another arrow showing reserve through email system, or maybe reserve through a information system. So those are multiple entry points, and this one may be physically going and getting the book. That's what I showed, explained here. So this state called being checked out has multiple entry points. I hope that's clear there. Like that you can, it doesn't have to be in all cases. It depends on the scenario, that's what I told. So maybe there could be in your system, if you have an object that has multiple states, if you have already identified that object, this particular object in your business domain can go through multiple states, but maybe they may have only just single entry point. So if it is single entry point, you don't have to show these circles. You can just simply put the arrow mark. In case it could come through many different points, then you have to show it in this format whenever it's entering. Okay, so the importance of state diagram we discussed. So class diagrams, object diagrams don't show you the dynamic. So in this case, developers in particular have to know how objects are supposed to behave because they have to implement these behaviors in software. It's not enough to implement an object. Developers have to make that object do something. State diagrams ensure that they won't have to guess about what the object is supposed to do. Right? Looking at the state diagram, you can simply understand what this object is going through, right? How it is changing. That idea you get it. You don't leave the person. So if you don't have a state diagram, for a changing object, it will be very difficult to guess, no? You have to keep on guessing how this is going to change, how this is going to do. And you have multiple places, it might have multiple ways of behavior. But if you don't have a diagram to show that, it's going to be very difficult. So state diagrams ensure that they won't have to guess about what the object is supposed to be. With a clear picture of object behavior, the likelihood increases that the development team will produce a system that will meet the requirements. Okay, so that was all about state diagram. Let me see. If I have missed anything. So I recommend you go through the VLE slides. So this is the same slides from your VLE from UCSC. Additional information, discussion here. Interaction diagram. So for example, most of the objects you might have something when you're designing a class diagram, you will have an attribute called status. So when you have this, if you have an object that has an attribute called status, that is automatically going to be a candidate for another state diagram. So with that particular object, you can start drawing a state chart diagram or a state transition diagram, which you can come up with multiple states. Hotel room, see that example I told. Hotel room can be in occupied, available, reserved. Course can be in open, closed, cancelled. So the UML notation for state, so sometime you may get this MCQ question. Keep a mind of the drawing. I think already in the beginning I gave you. So starting point is indicated like this, ending point is bullseye. A state is shown with this rounded rectangle. Keep in mind rounded rectangle, and also transition is shown through an arrow mark. It is shown here. Start, stop. Activities I mentioned, entry. So what are the three types of activities? Within a state, three types of activities. What did we discuss? Anybody can type? Right. Entry, exit, and do. Yes, exactly. Here in the slide, they have mentioned how do you show do. Now we saw two examples. When you're showing do, you put do slash and the particular event or the activity, or sometimes you can even use do colon that particular activity. In extreme cases, you can do something like this. The behavior in activity, entry action or exit action, can include sending an event to some other object. There could be something that you are passing to the other object. Maybe as part of, for example, your state diagram is basically representing only a single object. It is going to show the transition that is going to happen from this object to another. Let's say when it is moving to another state, then at that point, as part of the activities, your object can be talking, could be sending messages to, there could be an activity that is talking to some other object. That means which doesn't have a state, or it might be some external object. In that case, you have to show what is the thing you're calling and what is the event you're passing and any arguments. So this could be the format how you show that activity. with a mark like this in the front. Then you have the entry or exit action with the argument. So target is object receiving the event. So which object you are going to call. So the event could be the method you are going to call, and arguments could be what are the parameters you are going to pass. So basically it's like calling the object, that external object, with the relevant method. So sometimes you can show it like that. So for example, in this course activity thing, I think as part of course of opening, for example, as part of this one, you have entry and exit. Maybe the do activity of this would be, right, when you say do, there could be a do activity. That do activity could be this one, where it is calling the course roster object's create method. So this create method is there in the course roster object, and it is calling that. So to show that you may use a format like this, right? Substates we discussed, concurrent states, why it's important. Okay, that's all I have for discussing today. So with that, when this chapter 7 is concluded, we have a couple of more diagrams to discuss. I will discuss in the upcoming sessions. Any questions so far? Others? Okay.